regression, and finally logistic regression. So first we are going to discuss about linear model for classification. So here in this linear model for classification, our goal is to classify input vector x into one of k classes similar to regression, but the output variable is discrete. Input space is divided into decision regions whose boundaries are called decision boundaries or decision surface. Linear model for classifications. Decision boundaries are linear functions of input vector x. So in this diagram, we have decision boundaries. In these decision boundaries, under the decision boundaries, we classified some blue color rectangles. Above the decision boundaries, we classified some red colors shapes. Classifications. First, we need to understand about classifications. It use an object characteristics to identify which class or category it belongs to. That is, we are going to identify the objects based on the characteristics, and we are going to classify based on the characteristics. Example, whether a mail is a spam mail or a non-spam mail, whether a patient is diagnosed with a disease or not. So here we have given some of the example for classifications, some of the figures. That is, here so many diagrams are given. All are doing the classifications with the help of boundary curve, boundary regions. In something, there is say shapes are classified under the boundaries are one category, and above the boundaries are another category. So here also I have given one example. Here we have two kind of fruits. One is apple, another one is orange. So based on the weight and some other characteristics, here we classified the two shapes based on the weight factors. So here linear boundary decision arrow is available. Under this arrow, that is boundary arrow, apples are categorized, and above the arrow the orange fruits are classified. Here generally the classifier linear classifier is divided into three types: discriminant function type, probabilistic generative models, and probabilistic discriminative models. If you take the first one, discriminant function model, it's no need for computations of posterior probabilities. That is, in this method no computation of posterior probabilities, whereas in the another two model, probabilistic generative model as well as probabilistic discriminative models, we need to do the computation of posterior probabilities. That is, in the first category, discriminant functions directly map each x onto a class label, whereas in next two models, model class priors p of ck and the class conditional densities p of x bar ck, it used to compute posterior probabilities p of ck by x. In the third category, model posterior probabilities p of ck by x directly. So the tools using under the discriminant functions are least square classification and Fisher's linear discriminant. The tools using under the probabilistic generative model is Bayes theorem. Then the tool used under the probabilistic discriminative models are logistic regression. Here we are going to discuss about the pros and the cons of the three approaches. First one is discriminant functions are the most simple and intuitive approach to classify the data. It's a very simple model, and it is used to classify the data, but do not allow to compensate for class priors. This model not allow to compensate for class priors. Example, class 1 is a very rare disease. But it do not allow to minimize risk. Example, classifying sick persons as healthy more costly than classifying healthy persons as sick. Implement rejection option. Example, person cannot be classified as sick or healthy with a sufficiently high probability. So the discriminative model have some of the disadvantages. That's why we move to the probabilistic, the generative, and the discriminative model can do all that. Generative models provide a probabilistic model of all variables that allow to synthesize new data, but generating all this information is computationally expensive and complex, and is not needed for a simple classification decision. Discriminative models provide a probabilistic model for a target variable conditional on the observed variables. This is usually sufficient for making a well-informed classifications decision without the disadvantage of simple discriminate functions. Discriminant functions. Discriminant functions are functions that are optimized to assign input x to one of k classes. That is, here we are going to assign the input x to any one of the k classes. Here we have some one graph, that is the x-axis contains the features of x1 and the y-axis contains the features 2, that is called x2. Here we have one boundary that is called decision boundary. It is denoted by the red arrow. So in this decision boundary, the variables are that is greater than, that is y greater than zeros are above the boundary, and y less than zeros are comes under below the boundary, and y is equal to 0 is lies on the boundary. That is called discriminant functions graph. Then now we are going to discuss how to determine the parameters of discriminant functions. That is least squares for classifications. General principles. It minimizes the square distance residual between the observed data point and its prediction by a model functions. That is in this graph, that is the x contain x available in the x-axis and the t available in the y-axis. If the x is increasing, the y also increasing, then the point above the boundary is called as y greater than 0, and the point below the axis is called as x y less than 0. Then in the context of classification, find the parameters which minimize the square distance between the data points and the decision boundary. Here the problem is sensitive to outliers, that is also distance between the outliers and the discriminant function is minimized. It can shift functions in way that leads to misclassifications, that is some of the objects are not above the boundary or below the boundary, it lies on the boundary. That is the problem. How to determine parameters under the Fisher's discriminant? Here, the general principle is maximize the distance between means of different classes while minimize the variance within each class. So here there are two graphs. The first graph is maximizing between two variances. In the second graph, maximizing between class variance and minimizing within the class variance. That is maximizing between the class variances and minimizing within the class variances. Probabilistic generative model is the second model. This model contains the class conditional densities and the class pairs. It used them to compute posterior class probabilities according to Bayes theorems. So in this graph, it is the inverse of sigmoid function is the logistic function, which represents the ratio of the posterior probabilities of the two class. Probabilistic distributive models, logistic regressions. So in this model, the posterior probability is directly assuming that they have a sigmoid shaped distributions without modeling class pairs and class conditional densities. The sigmoid shaped function is model function of logistic regressions. First, nonlinear transformation of inputs using a vector of basis functions, that is pi of x suitable choices of basis functions, can make the modeling of the posterior probabilities easier. For example, if you take the p of c1 bar pi equal to y of pi equal to rho of w power t of pi, p of c2 bar pi equal to 1 minus p of t1 bar pi. Probability distributive model, logistic regressions. That is parameters of the logistic regression model determined by maximum likelihood estimations. Maximum likelihood estimations are computed using iterative reweighted least squares. Iterative procedures that minimizes error functions using mathematical algorithms. That means starting from some initial values, the weights are changed until the likelihood is maximized. How to find the best model? The approximation of the normalization constant Z can be used to obtain an approximations for the model evidence. Consider the data set D and the models having the parameters. For each model, define likelihood of P of D bar pi I M.